Anyway, so, all right, let me, what I want to do is transformation of variables. Trans of variables. Lots of shorthand today, because this is just, it's kind of a fascinating thing that can be done with Maxwell-Boltzmann integrals in general, is that you can turn them into other things that can be useful. We've done velocity. What I'm going to do in class, we know what the Maxwell-Boltzmann distribution is of velocity. I'm going to turn it into momentum. On your homework, you turn it into energy. It's a slightly bit harder than the transformation I'm going to make today with momentum. The transformation of momentum is a little easier, but it's going to be the same path to doing it for energy that you do on your homework. So anyway, I'm hoping this will be a good guide. Okay, now to do this, let me write down the Maxwell-Boltzmann distribution in terms of velocity. And I've already, let me start with 4 pi v squared. I notice that sometimes I'm a little bit goosey-loosey whether I write m over 2 pi kt, or if I do 4 pi v squared first. Obviously it doesn't matter, but I do try to be consistent. And again, I'm a little worried that this is hard to read, so I'm working on my handwriting. I'm trying to write a little bit bigger. I think that might help. And okay, now I cannot forget, now transformation of variables inside of an integral, I can't be forgetting the partial. Partials have units too. That's the spread, right? The spread, this is the probability density, that's the spread. Too bad it's a partial, it has to be integrated. And now that I have an integral expression, what I can do is turn this into other variables, but how? Now, in this case, what I'm going to do is momentum. You saw a little bit of that on your last homework. So I'm going to convert this velocity form to the momentum form. Now, there's 2 steps. Let's call this step 1. I'll just put a little 1 there. So you write down that step 1. Step 1 is to note that P is mv. So this already looks like it should be relatively easy. Now, the trick is to do this, I think you learned this in 8th grade. You learn to do this. P over m is v, right? So a little algebra. Okay, step 1 is incredibly easy. Wherever you see a v, squared or whatnot, write p over m instead. Right, so incredibly easy. Now, the reason for this is, now again, yeah, I'm turning this thing from velocity to momentum, and I don't know that I would necessarily know how to do that otherwise. And I'm going to go ahead and just do the simplification in my head. It's 2m kt. My m's look weird. Okay. So there you go. And I'm sure I can probably simplify that m a little bit. I'll worry about that later. It's not that big a deal, right? Here, let me. Don't want you getting confused. There you go. Okay, so what's cool about this is now it's in momentum, and I can start doing averages of momentum. I can convert velocity to a zillion other things as long as it's legit, and you're doing E equals 1/2 mv squared. So solve v is equal to square root of like e over 2m, something like that anyway. Okay. Also, the important thing about transformation of variables is that these are the same equation. This is the part that, if you get confused, I will almost guaranteed ask you a question like this on the exam. I do it every year because I think it's cool. And it shows that you are decently able in mathematics, which is kind of important. And the way to remember about, of course I'm going to give you the correct equations on the exam. The way to remember this is, it's the exact same equation. If you get confused what to do, this is exactly the same. That's v squared. This is e to the minus mv squared over 2 kt. It's the exact same thing, but here we have a problem. That's not p. Now, of course, like last time, who thinks I can just put it down, because there's a bunch of p's here. Let's just put it down. What do you think? Obviously the answer is no, because what the hell am I talking about? All right, now I promised you that I'm going to have to write d. I'm going to have to write d now. Now I promised you I would give you a very good visual representation, a geometry representation of what part of what a Jacobian is. A Jacobian is how you turn dv into dp. And I'm getting there. And I'm sure a lot of you already know that. I want to give you a visual representation of what's going on. Now, as you know, I like to graph things, and I like you to remember that integrals are not just some abstract mathematical exercise. They're areas under curves. And to do this, let's draw a bunch of rectangles. And if the rectangles were infinitely small, then, and I think I'm not doing this right, but anyway, there we go. There's our partial, there's our spread. Okay, when I go to Maxwell-Boltzmann momentum, it's pretty much going to look the same way. It's going to basically look the same way because, I've got a v squared, I still got a p squared. The exponential really hasn't changed. It's really still e to the minus ax squared. So I've got x squared e to the minus ax squared. It's going to fundamentally look the same. It'll be a little bit stretched out. It'll be a little bit stretched out because I multiplied velocity by mass, and let's say mass is greater than 1. So I'm drawing it stretched. If maybe mass is less than 1. It depends on the unit. Anyway, blah, blah, blah. So I'm going to transform this in a way that I stretch it out. Now, what I need to do is calculate the exact same area. Not that area will be 1, but whatever. I have to calculate the same area. Now that the curve is stretched out, the way I'm going to have to do that is I'm going to have to stretch out the partials. I've got to stretch out the partials so that, again, what I've done on top and what I'm doing here are exactly the same. So the change in momentum, the step has to be greater than the change in velocity. So that's the idea. Now again, hopefully a middle school student would understand what I just said. It's just that simple. But now here's my point to you. If you just say, oh, screw it, I'm just going to wipe that out and put dp, what you have not done, you haven't stretched out the rectangles. You haven't stretched them. They're actually the same original length. They would be like this. They're the wrong length now. And so I'm drawing a different graph. If I'm drawing a different representation, I'm going to get a different answer. These need to be identical. And if you don't properly stretch out the partial, then they're not identical. So you can't do that. So anyway, that's a motivation for why we have to do this in a visual form. Let me give you the formula, and then we're just going to work a bunch of examples. And I gave you this last time. We're going to have f of x dx, and we're going to transform that to, again, these are always in an integral representation. And I use g of y. So again, I'm hoping that this is helpful to you, that I want to make sure you understand that g of y is x. And so this is still f of x. Nothing changed. That's very important. Nothing changed at all. What can be a little hard is figuring out what's what. Now, this will obviously, let's make the example concrete. This will be velocity, y will be momentum. And that's why I had to solve earlier. That's why I had to say v is equal to p over m. That I have to do that, right? So anyway, now the next trick is I've got to have dx. I've still got to have dx. One way to do that is to write this, because that's dx. A over b times b is a. A over b times b is equal to a. This is dx. F of x dx. Nothing changed. That's the brilliance of this stuff. This, however, is, and I have two partials on top of each other. What's that? It's a derivative. Right, so derivative, remember you learned derivatives first and integrals second. Derivatives are a little bit easier. There's also an absolute value sign. That's because if the derivative is negative, that's like kind of a mistake. That means that you're running the integral backward. And that's just like a weird accident that you shouldn't let happen. So we put absolute value signs on that. And this, of course, is the Jacobian. This is the stretch factor for the planks of the integral, of the areas that are summed up to the integral, this is the stretch factor, so that the two graphs are actually, these two representations of the integral are actually identical, but you've got to stretch the partial, and that's what the Jacobian does. Okay, anyway, so this is the formula, it's on the cheat sheet, now you have to apply it. On your homework, you do it for energy. On the test, I have no idea what I'm going to do. I could do cats to dogs, I could do something else, there's no telling what I'm going to do, so you just have to kind of roll with this. Okay, now we've already figured out that x is v or v is x, y is momentum, and therefore this is g of, wait a minute. Okay, so hold on. So therefore, velocity is p over m. All right, so this is the thing. This is how you work this. All right, so you have this formula. You have this formula on the cheat sheet. Now you apply it. We're applying it to momentum. So what do? First, figure out what's your x and y. Because you see, you almost saw me get confused. Maybe you couldn't quite tell, but I did. I almost got completely confused. Identify x and y. Now we have to figure out what g of y is. This is where I can get a little twisted myself. Okay, the trick is, v is equal to what? Well, it's p over m. That's not too hard. And therefore, this is g of y. Right. X is equal to g of y. X is v is p over m is g of y. It's a very logical flow. I know I did that kind of quickly, but watch the video. Slow it down. All right, let's speed it up, I think. Okay. The last thing you have to do is figure out the derivative of dx, y. Technically, there's an absolute value. This is, of course, dg of y, dy. Because g of y is x. Okay, I've identified g of y. It's the change in p over m. Y is, of course, p. And this is 1 over m. There we go. Yeah, so what we end up with is, God, I hate to do this to you, but I tell you what, I'll rewrite it. I was about to do what I put up there, but I'll rewrite it. So that's cool not to. I've got 1 over 2 pi m kt to the 3 halves. And then actually, no, I can't do that. I can't. That actually, I'm writing the right formula, but I'm jumping ahead. 4 pi, what the hell's wrong with me? P squared over m squared, m over 2 pi kt, 3 halves, e to the minus p squared over 2 m kt, 1 over m, there's your Jacobian. There we go. That's how you do that. You do that, write that down, you're done, and what it ends up being is 4 pi. See, I've done this so many times I can actually simplify it in my head. That I remember from your last homework you had the formula. 3 halves, e to the minus p squared, 2m. And you probably, a lot of you have already noticed that when you transform this to energy, that's like question 3. Question 4 then has you calculate the average energy using the maximum Boltzmann distribution with energy as opposed to momentum, meaning I gave you the answer. The next question then has you use the average energy. I gave you the answer. I told you the next homework is the easiest one you have because I keep giving you the answer. You know I like to do that. So anyway, there you go. If I'm asking for average momentum, multiply that by momentum. Look for the integral of x cubed e to the minus ax squared. Yeah, there you go. So not much to this. Just just don't mess it up. Let's see. Actually, tell you what. What did I say? Let's do it. So I often have you do this. You see me do it on your homework, and again, I will likely do this on the exam. Maxwell Boltzmann is a big part of the first exam because, to be blunt, it looks complicated, but it's actually easy, and you know I really like to ask questions like that. It's, of course, correspondingly frustrating when you miss it, but can't help that. The same thing when I took it when I was your age. So let's do one thing with it. Now you can show that it's normalized, but I guarantee. So that's another thing. If you've done this right, you actually have a way of checking it. Look at the spare sheet, the spare sheet I give you on the exam, and check whether it's normalized. It's the same equation. It should still be normalized. It will be. And I'm not going to do that. Let's do this one instead. Let's do average momentum. And that ends up being, don't forget, it's momentum times Maxwell-Boltzmann of momentum. I'm not even going to write the whole thing out again, because what you really need to look for is this. What you need to do is look for this on the cheat sheet. Now, I also know that it can get confusing what the limits are when you're confronted with any new Maxwell-Boltzmann equation, or even the ones we've done. I know it's confusing what the limits are, so I'll always try to make sure that it's expressed. I'll try to make sure that you know what it is. And that's a big part of finding the right equation, the right identity of the cheat sheet. It's make sure you've got the right x cubed or whatever, make sure you've got the right limits. And when you see it, the one you think you need, then you probably got it right. And this ends up being hideous, right? Now these get pretty awful as you go up the ladder in terms of x cubed and x to the fourth and yada yada yada. Actually, it's odd ones that are a pain. Also note that A is a little different when it comes to momentum. If you look at that Maxwell-Boltzmann, it's a little bit different. It's not m over 2 kt, it's 1 over 2 mkt. Again, just look at your equation and just map it. It's a middle school skill. You should be able to do this. Okay, and therefore the average momentum is, don't forget the constants, as I warned you, especially as you saw on number 10 on the last homework, which probably got a lot of you. Don't forget all the stuff that's already there, the 4 pi from the geometry factor, the 3D Jacobian, now that you know that it's a Jacobian. I almost wrote down the wrong constants. It's 2 pi mkt. Okay, so these are already there. Okay, then you look at the, whoa. I wrote down that's the wrong identity. That's for the square. That's the square. Sorry, I'm not looking at, oh God, sorry about that. Bad me. This one's easy. Yeah, the odd ones are easy, the even ones are always a little bit more complicated. Sorry about that. Sorry, anyway. 1/2 a squared, so that's going to be 2 mkt squared. Yeah, there you go. And now what? What do you do? This is an exam. I just asked you this. What do you do now? What do you do? Huh? What could you do? This is number 9. There's 10 questions. You've just written this. What do you do?
Proper balance?
No. Go to number 10. That's the answer. This is the answer to number 9. Go to number 10. You're done. Don't linger on this. You're finished. All right. Now, I'm glad you said that. You said add bounds?
Yeah.
I have seen people do that. Don't. Why not? Okay. This identity, all right, this is equal to that. Why don't I have bounds on this? So I'm saying don't do it, because there's no bounds on here. But why aren't there bounds on here?
Because you're changing it back.
No, because it's already been done. This is the answer to this. This is the answer to the definite integral. Bounds have already been applied.
No, well, I'm talking about before you even, because you have an infinite integral.
Well, here, right, you mean, I forgot to write that down. Yeah. No. What I see people do is sometimes I see people try to do this.
Oh.
Right, and they try to figure out what's, sometimes they'll go for t and put t infinity. No. Again, that's the second most common mistake. First most common mistake is to forget that this stuff was there. Second most common mistake is to forget that this is the actual answer. You don't need to apply any weird limits, not that you could. And the other mistake is to try to simplify this SOB when I don't require you to, because if you simplify it correctly, you haven't gained anything, but if you simplify it incorrectly, you force me to take a point off because you screwed up and the plant exploded or whatever. So, but it can be simplified, but whatever, I won't do that. All right, anyway, so let's move on. Now here's the thing. This is where this actually gets unfortunately kind of painful. 1D Jacobian, so you understand this, right? And you do, and you get the geometry, how you erase it, right? It's not hard, right? I mean, a middle school student could understand this. Maybe not quite the integral part, but I think they can understand stretching and compressing things and scaling, right? That all makes sense. Where this unfortunately can get way more difficult is when you're in 2 dimensions. So we're going to do 2 dimensions, and then 3 dimensions is just is a step up from there. There is unfortunately a big leap going from 1 dimensions to 2 dimensions. 1 dimensions, again, is easy. 2 dimensions ups the ante in a way that all of a sudden you may think that you don't know what to do, and to be blunt, you kind of don't, all right? To be honest. So let's go from integrating f of x and y, which of course have partials of x and partials of y, so I better write 2 integral signs, to something different. F of, what am I doing? U and v, and of course, I better have partials of, sorry, I'll put that in order. U partial of v. Okay, how do I do that? Well, Jacobian. Okay, first thing is, of course, you've got to figure out that in some snarky way, I'm going to let you know what u is as a function of x and v. And x and, wait, v, what am I doing? Y, x and y, sorry. I'm just getting all my letters. U and v, x and y, sorry. Okay. So again, you have a 2-dimensional integral. It's an x and y, and you're transforming to u and v. And of course, I've given you the information of what u and v are. X is position, y is velocity, u is momentum, and v is energy. It's all sensible, right? Okay. So this is how you transform the function. You're going to use this information. It won't be particularly difficult. But now you've got the Jacobian part. So how does that work? Now, don't write this down, especially all of you on video land. I'm going to show you what's wrong. So don't put this. But I know what you're tempted to do. You're tempted to do, if you go from partial x, partial y to what? The Jacobian, du, dv. What is the question? Is it this? I'm tempted to do this. Change in u, change in x, change in v, change in y. Absolute value, because, and that's just because, again, if you accidentally pick up a minus sign, then the integral runs in reverse, and that's like way off. Okay, what do you think, right? Because that didn't look too bad. Because I've given you as a function of x and v as a function of y. Huh? That's right, I mean, they're scaling factors, right? You multiply, I mean, look at this. See dx, dy? Look at that. See, it's, oh, that is bad. It actually, yeah, it's actually off. That doesn't work. Oh, no, wait, no, hold on. What did I do? No, I should have done this, right? Dx, du, dy, dv. I should have done this. And you see it looks okay, right? Doesn't that look okay? All right, here's the reason. U is not necessarily a function of just x. It's got x and y in it. And the same for v. So you can't necessarily just, I mean, you can do that derivative, it's just not very meaningful. Besides, what if I just changed the letters? What if I made what I call u of v, and if I made v u, then those derivatives would change. They would change radically, probably. Well, that certainly seems arbitrary, and you can't just arbitrarily change functions. You can't, that's just absurd. So the answer is, as much as this kind of looks like our 1D case, just two derivatives, I guess I just multiply them? No, that doesn't work. Here's why. Now you recall that graph I made, I hope you liked it, where I was talking about, here's a 2D function, it's a plane, because it has to be, and it's integrated over a partial along x and a partial along, sorry, this is the x-axis, this is the y-axis. So this is the partial along x and this is the partial along y. And what you've got is those two partials multiply into an area. And then you get the area under the curve, right? So you get like a volume. And in the integral, this two-dimensional integral is this volume, and then you step along, and there you go, and you add up all the volumes. What's happening when you change from x and y to u and v? That area is changing. So it's no longer a step that's too big or too small. It's now an area. When you go to from x and y to u and v, the area changes. In fact, I found this website, and I'll see if I can link it, where this nice square can distort to like a trapezoid. Anyway, it gets all jacked up. It gets all jacked up. So what you need is a geometry factor that can take some jacked up trapezoid and turn it back to a square so that the integral didn't change. Okay, to do that, you, again, I saw this website that graphs all this, and so I'll link it, that shows you that the following formula is a normalization factor for areas. That's what's actually happening. So you know that the answer here is the absolute value of the determinant of a matrix. The matrix looks like this. Du, dy, dv, dx, dv, dy. Okay, here's a matrix. The determinant of that matrix is this times that minus that times that. Of course, there's an absolute value, just in case you get a negative. And now my point to you is the part where I'm hoping that you've seen something new here, is that what this is an area normalization. Something that takes a distortion, it like takes a square that gets all distorted and it puts it back to normal. Okay. Absolute value in the event that it just randomly comes up to be negative. So it's kind of close, right? But how did I put this? Anyway, I think my earlier description was a little jacked up. But anyway, so that is the proper, that's the proper expression for this thing. And therefore, the real expression is f of u and v, the u, dx, d, dy. It's kind of interesting that it permutes. Notice that the derivatives are permuted, and one reason I think that makes sense is that v and u are functions of x and y simultaneously, so I don't know how else you could possibly avoid that. Okay, so there's the proper expression. Okay, now the reason I'm battling on and on and on about this is, again, 1 dimension to 2 dimensions is a big change, because you now have to start working with matrices and determinants of matrices. Again, determinants are just diagonal cross minus the caddy corner cross. not much to that. 3D is a little bit more complicated. Whenever I want to look up a 3D determinant, I just Google it, and I look at it, and there's images on how to do this. Again, you hopefully had it maybe even in high school. It's unfortunately way more complicated than 3D, but it's in algebra hard. Also, I just want to point out that determinants of Jacobians, what's that?
The same way you do a vector.
Well, you tend to learn this in vector calc, right? So, and as a vector, again, what I want to point out is that these are geometry factors that turn distorted squares into back to normal. And then when it comes to 3D, you are actually taking maladjusted volumes, D, E, F, G, H, I. I recall that it is actually A times the determinant of E, F, H, I. And of course, this is well defined, EI minus HF minus B DF. And hopefully this is just a visit down memory lane. And again, what's kind of neat about this is if I can find and link that website that shows you a little bit better than I can on how these are just geometry factors. Certainly makes a lot more sense than it's just a formula that works. And I hate working with formulas that just work. So what about this? This is how we switch to spherical coordinates. So when we get into quantum, and God knows we are starting on quantum actually in exactly 1 week. Next Monday and Wednesday is just a warm-up to quantum. It's just some facts about electrons and light bulbs. That's actually what we're going to cover Monday and Wednesday. On Friday, we start doing quantum mechanics. Quantum mechanics has to be done in spherical coordinates because atoms are spherical. So one reason I want to cover this is I want to get you used to this. And especially the coordinate system, because it may have been a while. I obviously have to refresh my own memory of this every time. The angle in X and Y is theta. The off-axis, the length is R. The angle from the zeta direction, Z direction, is theta. It is phi, theta in X and Y, phi is how the flagpole has been over, and R is R. So there you go. Now I can also remember that X is R times cos. By the way, and remember on day 1 I mentioned to you that you might want to look at homework number 7. Cosine. Yeah, I knew I'd done something wrong because I knew that I had to have both angles. So you might want to look at homework 7 and don't throw up on yourself because you're going to be shocked at all the angles. I have pages and pages of expressions with angles because you're manipulating the quantum mechanics in spherical coordinates. And it really is, it's awful. I mean, there's no other way to explain it. It's just, it's an algebraic nightmare the likes of which you have never seen. And so again, one reason I'm going off on all this is I want you to get warmed up to that, get comfortable with R, theta, and C, because when we get into the quantum mechanics of rotation, which is important when we cover atoms, because atoms are round, you get into a soup of thetas and phi's that will blow your head off. So I want you to at least just get used to it. So you'll even notice on homeworks like 4 and 5, I actually start having you do some mathematical analysis of angles just for the hell of it, even though we won't have gotten there yet. Now you can imagine that as it's applied to this class, where we dealt with this was, we've already dealt with this. I just didn't quite show you. ddx, ddy, dvz. And we want to convert this to r, theta, and phi, where r is actually the net velocity, v. How did we do that? Don't forget these are all minus infinity. Okay, the way we did that was to convert to a Maxwell-Boltzmann of net velocity, theta and phi. Then we've got the Jacobian. The Jacobian, where the hell do I have that? Here we go. God, this is awful, right? The thing to remember is, I know I shouldn't say that so much, but all of these, any one of these is not particularly difficult. It's just that it's so much. And that's what really slays you. I've been doing physical chemistry at a PhD level for 20 years, and I can honestly tell you that there's only one time I ever ran into a mathematical something where I was like, oh my dear God, I have no idea what to do. All the other times I have run into mathematical expressions, which again has basically been my whole life, none of it has been difficult beyond the fact that it's huge. But huge is often just a bunch of freaking constants. And I can deal with that once I just recognize that I'm just multiplying kb times r times 4 pi times on and on and on. And then I've also got to do the integrals right. Let's see. The inner is 0 to infinity. The theta is 0 to, the next one is theta, that's 0 to pi. I have to look these up every time. 2 pi. So there you go. So now you can imagine on last Friday, you see why I did not necessarily want to start doing this in class on our first week, and why instead we're almost done. We're out of time. But here, let me just write down the answer, which I've already done. Right? You've already seen this. What you end up with is the Jacobian ends up being 4 pi v squared. So what you end up with is v squared, Maxwell-Boltzmann. Then you've got the integral from 0 to 2 pi of theta, and from 0 to pi of phi, because the Jacobian is how do I want to do this? Sorry, Jacobian ends up being, just for, I do have this worked out on the, sorry, I made a minus b squared. I made a bit of a mistake here. I forgot my sign. Sorry, I know I've gone over. So all of this SOB right here is minus v squared sine theta, sine phi, and this just ends up being, if you evaluate this, which I actually had you do on a homework assignment, by the way, coming up, what you end up with is your familiar expression 4 pi v squared. Which again is the formula for the surface area of a sphere times the net, which gives you a thickness, just like I said last Friday. But so instead of solving this with like a geometry representation, I just wanted to show you exactly how it's actually done by turning to r theta and phi. Understanding what a Jacobian is, I actually show you all the terms and how the determinant devolves into minus v squared sine theta. There's an absolute value sign, so the minus goes away. Triple integral, that just gives 4 pi. It's not terrible. Anyway. All right, so that's that.